transport of energetic electrons in the radiation belts, understand them, quantify the loss, determine the balance of the accelerations, and understand the dynamics associated with geomagnetic storms. And I really want to emphasize this mission because there's a lot of VERSIM relevant science that we can link to the radiation belt storm probe's mission. For example, they're going to be making measurements of plasma waves in the VLF range. And many of us are interested in this, have been very active with this, and Craig Kleitzinger from the University of Iowa is leading that instrument, as Andre talked about. They're also going to need to know about plasmaspheric cold plasma densities so they can understand about the properties of those waves and how those waves can interact with radiation belt particles. And that's an area in which VERSIM is interested in. And also, if we're talking about the acceleration and the loss of the radiation belt particles, the interaction between the waves and the particles, that's a fundamental science goal of the radiation belt storm probes, and is an area in which the VERSIM community has been working for decades. So here's a really fun opportunity, a really interesting opportunity for us to link to two big, new, expensive, shiny space missions which will collect really cool data. And we should be able to work with those people and do interesting things. There is also a hope of some more missions that will be launching in similar sorts of times: the Russian Resonance, the US Air Force DXX, and the Japanese ERG, which may be up at similar times to the radiation belt storm probes, or may come a bit afterwards. So there's multiple missions which will be making relevant measurements, and if we're working in this area, we're going to have cool data to play with for probably the next decade. So it's a good area to be in. Now, one of the science goals of the radiation belt storm probes is to understand and quantify the loss of electrons from the radiation belts. And it turns out that the radiation belt storm probes aren't very well suited for this particular science goal. None of the instruments on board RBSP can measure loss. You'd like to think there should have been, and some people suggested some instruments like that, but none of them actually got put onto the spacecraft and flown. So one of the attempts to try and meet the science goal is from missions of opportunity. And one example is Barrel, led out of Dartmouth University. That's the balloon array for RBSP relativistic electron loss. They are going to launch balloons from the Antarctic, and in fact our colleague Andrew Collier is hosting one of the launch sites, and so is Mark Clilverd for the British Antarctic Survey. They're going to launch balloons. The balloons are going to drift in the wind around the Antarctic, and they're going to try and keep an array of 4 or 5 balloons up in the air at all times, so they can measure the particles when they come out of space, smash into the atmosphere, go splat, 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 and from the balloons they can look up and detect the X-rays coming down. So the Barrel campaigns are going to be trying to make measurements of loss at the same time that RBSP is flying up there in space. Those of us who don't have access directly to spacecraft and don't have access directly to balloons can still make a contribution. Many of us make ground-based measurements, and many of those measurements can be used to quantify loss of relativistic particles from the radiation belt. So we've got an opportunity to collaborate here. And in today's talk, I want to talk about the sorts of ways that we could do that. So recently, I undertook a study to try and understand how different ground-based instruments using the ionosphere as a particle detector will respond to energetic precipitation. And I used VLF subonospheric propagation, rheometers, and GPS measurements of vertical tech. So let me remind you about how these work. Here's my cartoon of what's going on. Imagine we have the technique that's been talked about previously. We have a VLF transmitter propagating to a receiver. The waves propagate under the ionosphere, so that's sub-ionospheric propagation. If there is particle precipitation, these particles come out of space, they zap the ionosphere. They change the electrical properties of the D region of the ionosphere. That changes the Earth ionosphere waveguide, and therefore changes the properties of the waves, and it will change the received amplitude and phase. So with VLF subonospheric propagation, we should be able to use the changes in amplitude and phase to determine what the changes in the D region are, and Steve Kummer gave an example of that in his talks, and from the changes in the D region we should be able to work out what came out of space to cause those changes. Now another example would be rheometers. Rheometers are another relatively cheap, relatively simple instrument, but instead of looking at a big powerful VLF transmitter paid for by other people, you use the stars, provided completely free, the radio noise that comes from space that is absorbed in the ionosphere. And you look for changes in the absorption as that HF radio noise comes through the ionosphere. And the thicker the ionosphere, the more absorption there will be. And so once again, zap that ionosphere, build up the electron density, you'll get more absorption. And so with a rheometer, you have the possibility of measuring precipitation above your heads. Finally, I wanted to mention this GPS-derived VTEC, vertical total electron content. And that's because that's an area that a lot of people are getting into. There are arrays of TEC, arrays of GPS receivers which can be used to derive vertical total electron content, which is just an integration of how many electrons there are between you and the spacecraft. Okay, and it should be true that when particle precipitation occurs, this should lead to more electrons in the ionosphere. And so it's possible that that might be used to measure particle precipitation. Although we have to go see whether or not it's practical. Various people have said to me, oh, I want to do this. In fact, they've gone away and bought instruments to put them in to measure particle precipitation. So I wanted to build the tools by which I can extract the fluxes coming out of space into the ionosphere on the basis of the measurements made of our radio waves on the ground. I wanted to be able to build the tools by which I can predict what fluxes must have come out of space. And that's what the basis of this paper is, and if you're interested in the finer details, it was published in Radio Science a small number of months ago. Okay, so when those particles come out of space, as I keep doing, okay, they strike the ionosphere, and for the sort of energetic particles that come out of the radiation belts, they will deposit most of their energy into the D region of the ionosphere. Okay, so from a 20 keV electron will deposit the majority of its energy at 90 kilometers, a 100 keV electron will deposit the majority of its energy at about 80 kilometers, etc., etc. The more energetic, the deeper the electrons can penetrate into the atmosphere. So in a sense, the atmosphere is acting like a mass spectrometer. Okay, it's differentiating the different energies as they reach in and drive increases in ionization rate, which should be reflected in ionization density. If you want to do this, of course, you have to start off with, you take the flux that's coming out of the sky and you hit the atmosphere with it. Now, you can use various expressions that you can get out of textbooks. There's a book by Rees, for example, by which you can convert the incoming electron energy flux and produce an ionization rate. So that's fine. You've got an ionization rate in the atmosphere, but our instruments don't respond to ionization rate. They respond to charge density, electron number density. So we have to go from ionization rate to electron number density. And in the middle, there's some sort of chemistry. Okay, stuff is happening. The electrons are getting flicked off. Some of them are being captured. Some of them are floating around, being free. I mean, stuff is happening up there. I don't want to build a large, complicated chemical model because it turns out that they are really large and complicated. But I have friends who do this sort of thing. So I collaborated with the team from the Sadankala Geophysical Observatory, who have built a D region ion and neutral chemical model that has hundreds of reaction pathways. Hundreds and hundreds of the solid things. Like, it's really complicated. And I tried to build empirical expressions, really simple expressions, which agreed with their calculations, but didn't require me to trace hundreds of pathways. I only care about the electrons. I don't care about the ions, I don't care about the ozone, I don't care about anything else. I want to make electrons and then know what the balance will be. When the ionization rate goes up, what will the new ambient electron density will be. And this is my results. So we took a set of constant ionization rate increases. So you have a constant ionization rate increase at all altitudes, and then you run the Sedunkler ion and neutral chemistry model, the SIC model, to produce an electron density profile. Then I got some simple empirical expressions, some weighted expressions, to try and fit their model. And the dotted lines here are my calculations, and the thick lines are their calculations. And for some of you, you won't be able to see the dotted lines because I think I did a really sodding good job. Okay, with much tweaking and fiddling in that, I've managed to mostly, it's not so good at the very highest altitudes and the various highest ionization rates, but for the most part, I can empirically fit the expected electron number density. And my expressions are pretty fast, whereas the SIC model is quite slow to run because it's got hundreds of chemical pathways it has to follow. So in my expressions, which I just run in MATLAB, it's quite easy for me to use those to make the calculations I want where I'm focused on the radio waves. Once we have a modified profile, so we start off with an ambient electron number density profile, and then we zap it. That will then produce a changed profile. Once we have a changed profile, we need to determine what will that look like to our instruments. How will that affect the rheometer absorption, the VLF propagation, the total electron content? So for the VLF propagation, I'm going to use LWPC, the long wave propagation capability code from the US Navy, which has been talked about by several authors, to determine a change in amplitude and a change in phase. For rheometers, I'm going to use well-known expressions for determine the O and the X mode, which for a wide beam, they can be combined to get the total absorption. And for a GPS, vertical total electron content, it's actually a lot easier. You just add up all the electrons. It really is just an integration of all the electrons in the beam. If you're going to do this sort of thing, of course, we have to pick a modeling point. We have to determine some profiles. So I'm going to pick a location in Island Lake, Canada, and I'm going to do that because I already have a VLF receiver in Churchill, Canada, and we're monitoring a transmitter in North Dakota, which the Great Circle Path goes more or less over the top of Island Lake, and at Island Lake there is a rheometer, and there's a magnetometer, there's a whole lot of instruments there. So I'm sort of trying to model the real world. I'm also, later on, going to show you some calculations made for NAA to Churchill and from NAA to Sedunkler. In terms of the ambient profile, I use the IRI, or IRI, International Reference Ionosphere, for the high altitudes. As we know in this community, IRI is not very good at the lowest altitudes, which are really important to VLF propagation, and so I use measurements that may undertaken by Neil Thompson, and then I join them up in a slightly arbitrary way. But the red line here is from the IRI. This line here, the blue line, is the suggestion from Neil Thompson, and you can see that they're not so bad. You can combine them in a way that's not horrible to produce a background electron number density. And now I start zapping the ionosphere. So first of all, let's assume that I'm considering sub-ionospheric VLF propagation. I need to consider day and night separately, and I need to consider amplitude and phase separately. And I'm going to start off by looking at monoenergetic beams. Now, this isn't like reality. In reality, you don't get one energy coming out of the radiation belt zapping into the atmosphere. But in terms of trying to understand the sensitivities of the three different approaches, this is a manageable way to move forward. So let's imagine that that there's a monoenergetic beam. Energy is on this axis, the intensity of the flux is on this axis, and you can see down here in this part where the fluxes are small and the energies are small, there is no effect. The VLF does nothing. Up here, where the energies are large and the fluxes are, the energies are large and the fluxes are small, the VLF does nothing. Up here, when the energies are large and the fluxes are huge, the VLF goes crazy. The question is, at what point can I first start to detect a change? Now for VLF, of course, we are working with a waveguide. So if you throw in a 10 keV electron, the energy is deposited above the normal VLF reflection height. It doesn't matter how much flux you put in there, the VLF instrument will not respond. It's all invisible up there. It's above the reflection height. And when you do the calculation, it turns out that the minimum detectable energy for VLF subionospheric propagation is about 50 keV for night and about 150 keV during the day. Because of course the reflection height changes from day to night. So that's an interesting sort of number, because I've always waved my hands and said 20 to 50 keV. But when I actually do it properly, I find that it's a bit higher. We could put in, just as an indication, some lines to suggest the minimum energy for day and night and the minimum fluxes that are used, that are necessary to trigger our instruments. Now, of course, with subionospheric VLF, as Ken Lin was telling us, because it's a waveguide situation, if we change the length of the path, if we change the frequencies, we change our sensitivity. Not our minimum energies that much, because the reflection height for VLF is basically the same, but the flux that's needed for us to be able to detect the change changes a lot. So if I take, in this case, NAA to Churchill and NAA to Sedunkler, I find that the minimum energies are fairly similar, but the fluxes are really different. For a long path, like from NAA on the east coast of the US to Sedunkler, a much smaller flux applied to the whole path will produce a detectable change. For a short path, I have to hit the path much stronger because it's so much shorter. Now, if we contrast this quickly with rheometers and the total electron content, I find that, for a start, I find that rheometers are actually more sensitive to precipitation during the day than the night. And for VLF, it's the other way around. This is because for rheometers, it's a combination of the collision frequency and the electron density combined. And so rheometers are actually more sensitive to precipitation during the day than night, but there isn't a minimum energy at which they detect anything because they're passing through the ionosphere. If you hit that ionosphere at 100 kilometers hard enough, it will see it. Now, if we contrast with the VLF technique, we find, I'll just move on now to, if we move away from monoenergetic electron beams to a real beam, an actual range of energies. So I'm going to take an energy spectra reported by Clilverd et al. From the Demeter observations and sweep through my NDK North Dakota to Churchill path, and I can work out the sort of fluxes I need to produce a detectable signature, a detectable change. It's about 1 electron per cubic centimeter per steradian per second for nighttime and about 50 for daytime for the VLF. If we contrast that with the rheometer, we find that I need to have 10,000 more flux, so 4 orders of magnitude more flux during the nighttime and 10 times more flux during the day to produce a detectable response. So the rheometers, they're fine, they work, but you need to hit the ionosphere really hard for it to be able to detect something. VLF is actually more sensitive. In terms of the vertical electron content, no way. You just can't get a measurable change with a realistic electron precipitation. And so, for example, if we take this period here, this is some work that Mark led. He took a 160-day period in 2005, measured the amplitude changes in Sedunkler from the US Navy transmitter on the east coast of the US. And because the path was sunlit for the whole 160 days, we were in a good modeling situation. We could extract the electron fluxes from those numbers, which are given here. I can then use those to predict the changes in the rheometer and the VTEC. For VTEC, the biggest VTEC I get is about 0.03 of a VTEC unit, and they reckon that you need about 0.1 to get above the noise floor. So for a realistic range of fluxes, it's undetectable. For rheometers, however, for the big storms, I get detectable rheometer changes of 0.5, 1 dB, that sort of thing, but it's only for big storms. For your average, just sort of electrons dribbling down, which happens all the time, which we can see in the subionospheric VLF, the rheometers are generally not sensitive enough to do that. Now, very quickly, I'm just going to mention, we shouldn't write off the vertical total electron content measurements entirely, because it turns out that you can see substorm precipitation. Precipitation during substorms, which is much stronger than what normally comes out of the radiation belt. There was a recent experimental study by Watson et al. Coming out of Canada, who suggested that they were seeing changes of a few TEC units during substorms. And I'm not going to go through the details, but I'm going to say very quickly that when I did some modeling, I could produce vertical TEC changes of a few TEC units during substorms. So that's a really different situation where you can compare them with the radiation belt precipitation, where I was getting 1/100th of a TEC unit, which is unmeasurable. For substorms, I could produce something meaningful. But in those instances, I was getting rheometer absorptions of 3 to 5 decibels of absorption. Now, for those of you who ever worked with rheometer data, that's like a solar proton event. That's a huge amount of absorption. You might even think your instrument's broken when you see 5 dBs of absorption. And in the VLF, I was getting 10 to 15 dB decreases in the amplitude and 200-degree phase changes for those events. But I need to tell you, that's not just modeling there. These particular changes of 10 to 15 dB at 200 degrees of phase, we have observed for substorms occurring and measured in our instruments in the Antarctic. Okay, so in summary, so we're now in the process of trying to use our aardvark, the Antarctic Arctic Radiation Belt Dynamic Deposition VLF Atmospheric Research Consortia, to make measurements of precipitating electrons and working with the people who are flying RBSP and flying the barrel balloons. And there's many members of the aardvark consortia here today, particularly from South Africa and Hungary and Finland. Right, and that's the summary. The summary is ground-based instruments are interesting, but sub-ionospheric VLF is a good technique for measuring precipitation into the polar atmosphere, which will allow us to couple to all the exciting things that many countries are flying spacecraft to understand. And thank you very much, and sorry for going over time.
Any questions, please? Comments? Then I have a question. How can you compare, for example, if you take monoenergetic injection or injection with a spectrum, and if the energy flux is the same, how can you compare the influence of this injection, for example, on the sub-ionospheric propagation?
The change in the ionospheric profiles will be different, because if you've got a monoenergetic flux, it will only affect a small range of altitudes with a given energy flux. But if it's got a range of energies, it will stretch out over a wider range of altitudes that it affects, and so you'll get a different electron density profile, even though it's got the same energy flux.
Yeah, it's clear, but as for sub-ionospheric propagation of VLF signals,
for sub-ionospheric propagation, we do not have a particularly good way of extracting the energy spectrum. You can say, I can't model it right with a monoenergetic, I need a spectra, but normally we need some other instrument, particularly a spacecraft, to give us an idea of what the spectra should be. I wish I could, but at the moment I can't.
Other questions? Thank you very much again.
Thank you.
We go to the next one.